Hi everyone and welcome to the new video. What you see on the screen is the yellow LED, and for you it looks yellow, right? But what if I tell you if there is no yellow component here at all? Will you believe me? In this video I will take a spectrometer, several light sources, and I will compare it to what we see on the screen. Without further ado, let's figure it out. First, let's look at the picture of the visible spectrum. It covers all the colors visible by the human eye, from the violet at the left part to the deep red on the right part. And I suppose there is nothing new here. These spectrum colors were discovered by Isaac Newton in the 17th century and we all know it from school. And now let's do a simple experiment. Here I have the yellow LED and I have a spectrometer. I point it to that LED and we see a yellow color. As we expect, this yellow color is located at the medium part of the spectrum, which is kind of obvious and what we expect. And now we can see the strange part. I am pointing the spectroscope to my monitor that also shows the same yellow color. And surprise, there is no yellow color at all. How can it be? Is it something wrong with the spectroscope, with an LED, or with the monitor? Let's figure it out. Okay, let's get started. As a first step, I will take a spectrometer and I will observe the spectra of the several light sources I have. As we know, the visible spectrum is going from 380 nanometers to 750 nanometers. The shortest wavelength we can see is a violet color. Its wavelength is about 380 nanometers. The even shorter wavelength belongs to the ultraviolet and obviously we cannot see it. And the longest wavelength is 750 nanometers. We can see this wavelength as a red color, and I will start with that. And here I have a red laser module. It is connected to a breadboard, and according to the specification it should produce a red color of the 650 nanometers. And now I'm pointing the spectrometer to this laser. It's not so easy because the beam is pretty narrow. And as we can see, we have a peak at exactly 650 nanometers. And here we can also try to make a fun experiment, and we can try to estimate the sensitivity of our eyes. Near this laser diode I also have a normal LED. It is also red, but its wavelength is slightly different. And I can see on the spectrometer that the color difference is about 25 nanometers. And I'm curious, will you be able to see it with the naked eye? Practically I barely see it, but how about you? Write in the comments below. Will you see the difference within two red colors? As we can see on the spectrum, the LED's color is 650 nanometers and the second color is 625 nanometers. Do you really see this difference? I think I can barely see it, but I'm not 100% sure and I will be curious to know your answer. And the next LED I want to show is a green one. It was easy to find it because it is on the same power supply. And as we can see, it really looks green with a wavelength of about 525 nanometers. After testing red and green LEDs, let's go to the opposite side of the spectrum and test the blue one. I have found an old PCB in my drawer and it is good for my test because it has a blue and yellow LEDs. Let's see how it looks. First, I'm pointing the spectroscope to the blue LED and as we can see, it is not surprising, we see a blue color. And now let's test the yellow one. And as we can see, its spectrum is correct and it's about 580 nanometers. Of course, I'm not going to test all possible colors, this video will be too long. And now let's start with the fun part. Let's test the computer monitor. As I promised at the beginning of the video, not all colors you see on the monitor are actually real, but how can it be? To see the difference, I will test the same LEDs and let's see how it looks. Instead of using the monitor, I decided to use my phone just because it's brighter and smaller and it is easier to point the spectrometer on it. And let's do the same test. To do this, I just have found this website, so it is easy to select the color and point the spectrometer at the screen. And first I'm selecting the red color. And as we can see, the spectrum is correct and the wavelength is about 630 nanometers, so it generally matches the LED. And now I'm selecting the green color and interestingly its intensity is bigger. Now I'm selecting the blue color and as we can see it is the left part of the spectrum. The wavelength is about 450 nanometers. And now last but not least, let's test the yellow color. And here we get it. Can you see what is wrong? As we can see, the result is really surprising. It surprised me at the first time and actually inspired me to make this video. I will pause the video for 3 seconds. Do you already see it? Okay, here is the answer. As we can see on the screen, there is no yellow color on the spectrum at all. How can it be? To find the answer, let's put all the spectra on the same screen. At the left part of the screen I will put all spectra from the LEDs, and on the right part of the screen I will put the spectrum from the phone. Let's start with the real spectra first. This is the red LED, this is the green LED, and this is blue LED, and this is yellow. And at the right part, here are the spectra taken from the phone. This is also red, green, blue, and yellow. And now we can see the pattern, right? As we can see, the monitor can produce only red, green, and blue colors. And it makes practical sense because technically there are no more LEDs inside. Here is a close-up picture and we can see it clearly. I can randomly choose colors on my phone, and as we can see, only the intensity of the red, green, and blue peaks is changing. But then the question remains clear. How on earth can we see other colors? What's going on here? For example, how can I see the yellow color if there is no yellow component in the spectrum at all? Apparently the problem is not in the screen and also not in the spectrometer. We need to figure out how our eyes work. Let's get into it. Okay, at this moment we were able to figure out that our monitors can only produce R, G, and B colors. And to understand how we can see other colors as well, we need to look into the human eye. Technically, the human eye works almost like a camera in your smartphone. It has a lens at the front side and photosensitive cells at the back side. Special cone cells are sensitive to the light almost the same way like pixels in your smartphone. And now we are coming to the interesting part. Cone cells are not the same, otherwise we will be able to only see the monochromatic image. So how does it technically work? Well, it turned out that in the human eye there are 3 types of cells, which are responsible for short, medium, and long wavelengths, as you can see on this graph. So how does it work? As an example, let's consider the S cone. On the graph we can see its sensitivity curve, and this cone cell is responsible only for short wavelengths. And mathematically and physically it is very interesting. First, the output of the cell is a single number. All information about the wavelength is already lost. Technically, we as humans are not sensitive to wavelengths. As an example, if we consider M-type cones, I can turn on the light with a wavelength of 530 nanometers or 580 nanometers and the output of the M cell will be the same. So how can we distinguish the colors? I think you already know the answer. Our retina has a big amount of cone cells that are mixed together, and our brain gets the color information by comparing the output of the nearby cells. For example, the light of 530 nanometers will provide this unique combination of M, L, and S cells. And we should not forget that the output of each cell is a single number, and in this number there is no information about the wavelength anymore. This simple fact actually allows monitor manufacturers to trick our eyes, and because of that we see the yellow color that in reality do not exist. How does it work? Look at this picture. This is a yellow color and it doesn't exist on the monitor. However, as we can see from the graph, this yellow color activates M and L cones. The monitor can activate red and green LEDs the same way, so it will provide the same output, and as a result we see the same yellow color. So practically you can curse me, but you cannot unsee it when you know it. All our screens can natively display only R, G, and B colors. From the physics perspective, all other colors displayed by the monitor are actually fake, and we only see it because our cones work this way. And by the way, is this system perfect? Actually not. Every monitor has its own color space, and monitors may have a limitation in displaying very saturated colors, but practically it's not a big deal unless you work on the design, then you choose a specific monitor. And practically very bright and vibrant colors rarely exist in nature. Maybe there are some tropical birds or insects, but we don't see it very often. So the color representation of our screens is practically good enough. Screen manufacturers are also doing their best in increasing the color quality, but as far as I understand, they still use this RGB model, And no manufacturers are adding additional colors like yellow LEDs as far as I know. If I'm wrong, write in the comments below. So it is interesting to see how it works. Understanding the cone cells also helps us to understand, for example, how dog's vision works. They have only 2 types of cone cells, not 3. And if you want to learn more, the color science is a huge area. There are different mathematical models, different color spaces, and so on. If you want to see more tests about this, write in the comments below and maybe I will make a separate video. And that's it for this video. Thanks for watching. I hope you learned something new. If you enjoyed this video, press the like button. I use this information to know if the topics are interesting for viewers or not. Also, feel free to subscribe to the channel and press the notification bell not to miss the future videos. You are also welcome to visit my Patreon page. This support helps me to buy things like this for testing. Thanks for watching and see you next time.